YouTube video for investigation 3A, which is called Incoming Solar Radiation. And both investigations 3A and 3B are actually going to be focusing on the energy that comes into the Earth and the atmosphere from the sun. This first investigation, 3A, is really going to be focused on the seasonal cycle on the planet. And so what I'm going to do here today is I'm going to take things in a slightly different order than the way the AMS presents it. I'm going to add a couple of graphs that are oldies and goodies from the AMS that they've taken out of investigations that used to be investigations for years and years. And hopefully, with any hope, this will create a fairly coherent discussion about our seasonal cycle. So why don't we get started on the PowerPoint, and let's begin our slideshow. So again, incoming solar radiation. Now again, like I said, this is really all about the seasonal cycle investigation 3A. So what we're going to do is I'm actually going to jump ahead and I'm going to discuss figure 3A2. And I just want to spend a little time, first of all, just discussing the definition of a day and then moving on from a day to a year. So in order to understand a day, you need to know that the Earth spins about its axis. And the axis is an imaginary line that basically connects the North and the South poles. And the Earth rotates about its axis once every 24 hours. So a complete revolution every 24 hours. And so that 24-hour period of revolution is what we define to be a day. And so the Earth is continuously spinning about its axis. And at the same time that the Earth is spinning about its axis day after day after day, it is slowly revolving around the sun. So if we take a look at figure 3A2, we basically see the Earth taking its annual cycle, its annual spin around the sun. Now the Earth doesn't actually move around the sun in a perfect circle. The orbit is a bit more elliptical. And in fact, the Earth is closest to the sun right after the first of the year, and it is furthest away from the sun right about on the 4th of July. Now, the reason I bring that up is because if the seasonal cycle were just a function of variations in Earth-Sun distance, then in fact, our summer would be in January and our winter would be in July. Not only that, but it would be summer everywhere on the planet in January and winter everywhere on the planet in July. And several of you probably know that the seasons between the northern and the southern hemisphere are reversed. So, for example, we are right now, I'm recording this video on the 21st of August of 2025, and we are in late summer here in the northern hemisphere. So in the southern hemisphere, it's actually late winter. We're getting ready to enter autumn, and in the southern hemisphere, they are approaching spring. So basically, we have a little bit of work to do still to understand what the seasonal cycle is and why we get the seasonal cycle we see on our planet. Now, in order to understand the seasonal cycle and the changes of seasons, we need to focus again on our axis. Again, this imaginary line that connects the North and the South poles. And the axial tilt that I have here, 23.5 degrees, is relative not really to the sun, but to the fact that the Earth actually traces out a plane when you connect a line between the Earth and the sun. So I'm going to define something now called the plane of the ecliptic. So imagine that we're taking a look at the sun, and the sun is shining directly overhead at a point somewhere on the Earth. And so basically, and this is true, that basically the sun is shining directly overhead at some point on our planet at every moment. Now, as the Earth is tracing its elliptical orbit around the sun, if we just imagine that this line connecting the sun and the Earth just is essentially tracing out a surface, a horizontal surface like a tabletop, what we'll see over the course of the year is that we get this nice oval-shaped tabletop or plane. It's just basically like a flat piece of paper that is in the shape of this oval or this ellipse. And we call this plane the plane of the ecliptic. So I have that right here on the right-hand side of our slide. Now, when it comes to the Earth's axis and the plane of the ecliptic, the Earth's axis is tilted 23.5 degrees relative to the plane of the ecliptic. And you'll see I have boxed in here 23 degrees, 27 minutes. So when we take a look at degrees and minutes, A degree has 60 minutes. And so the Earth's axis is tilted about, and we're going to say for our purposes, we're just going to say it's 23.5 degrees relative to the plane of the ecliptic. Now, it's not relative to the sun, it's relative to the plane. So if you are sitting looking at your screen, whether it's on a laptop, a desktop, or some sort of a tablet, what you're doing is basically you're being a satellite and you're looking at the solar system from your vantage point. And as the Earth is basically tracing out its elliptical path around the sun once every year, you'll notice that relative to the plane of the ecliptic, the axial tilt never varies. It's always 23.5 degrees, and the tilt is always in the same direction. Now, the reason this is important, and let's just start where I have our arrow pointing at the Earth. So we see on September 23rd that our arrow is pointing directly overhead at the equator. So here's our axial tilt, and the axis is essentially oblique to the sun. And we see that the sun shines directly overhead at the equator. Also from our vantage points in space, looking in at our screen, we see that half of the planet is illuminated by the sun. And in fact, half the planet is always in daylight and half the planet is always in darkness. So the daylight part is illuminated by the sun, and where it's night is basically where the Earth is being shadowed by the daylight portion of the planet. So whenever we're in night here in Ohio, basically it's night because on some other part of the planet it's daylight and it's intercepting the sun that we would otherwise be getting. When it's daylight here in Ohio, we're intercepting sun that would otherwise be getting to a part of the planet that's currently in night. So no matter when we deal with the planet and the sun, half the planet is always illuminated, half the planet is always in shadow, and it's night. So if you take a look at September 23rd, you'll see that the sun shines directly overhead at the equator. The axis is perfectly oblique to the sun. Now if we move around 90 degrees, roughly one season, what you'll see is that when we get to December 21st, which is the winter solstice, you'll see now that the southern hemisphere is tilted toward the sun, the northern hemisphere is tilted away from the sun. Here's half the planet in daylight, and here's half the planet in darkness. If we move around another 90 days roughly, and we go to the vernal or the spring equinox here in the northern hemisphere, you'll see now that again the axis is oblique to the sun. The sun is actually shining over the part of the planet that is on the inside of our screen, so we can't see the daylight part of the planet. All we can see is the half of the planet that is in night. And then if we move another 90 days, another quarter of the year around, now you can see that on the summer solstice in the northern hemisphere, June 21st, now we see that the northern hemisphere is tilted toward the sun, the southern hemisphere is tilted away from the sun. Here is the half of the planet that's in daylight, here is the half that is in night. So what you can see now is that as we go through the course of the year, the northern and southern hemispheres basically alternate from being tilted toward to being tilted away from the sun. And in between, we have our equinoxes when the axis is tilted neither toward nor away from the sun, it's just oblique to the sun. Now, as the Earth traces this ellipse and goes through its seasonal cycle in the course of a year, this also is going to have an impact on both the angle of the sun in the sky as well as the daylight period. And that's going to actually take me backwards in our investigation to figure 3A1. Now what 3A1 shows is basically the planet at 3 latitudes. The first latitude is the equator. So you've got, these are cartoons obviously, so you've got a person standing at the equator, and what you see basically shown in this figure is where the sun is located at the equator at noon. On these 3 dates, or actually 4 dates. June 21st, which is the summer solstice, March 21st, September 23rd, which are the equinoxes, and December 21st, which is our winter solstice in the northern hemisphere. So what you see at the equator is during the equinoxes, the sun is directly overhead. And when I say directly overhead, it is literally straight up. So if the horizon is right here where we have south, the sun is literally 90 degrees above the horizon. It is straight up, it is directly up in the sky. On the solstices, on June 21st and December 21st, the sun is still fairly high in the sky, but it's just a little off of vertical. And in fact, it's at 66.5 degrees above the horizon on both of these solstices. So the sun is always between 66.5 degrees and 90 degrees above the horizon. So not surprisingly, in the tropics, when the sun is always high in the sky at noon, the tropics are always basically receiving pretty intense energy from the sun. Now if we move here in the middle, this is 45 degrees north. And this is roughly Bowling Green, not quite. Here in Bowling Green, we're at about 41 degrees north, so we're just a little bit south of this. But you see that if we take a look at our 4 dates, so here's our summer solstice, our 2 equinoxes, and our winter solstice. Let's just start with the summer solstice. This is when the sun is highest in the sky here in Ohio. And in fact, at noon in Bowling Green on the summer solstice, the sun is about 72.5 degrees above the horizon. So it's still pretty high up. In fact, on our summer solstice, the sun is actually higher in the sky at noon than it is at the equator on the winter solstice and the summer solstice. So we actually get pretty intense energy. Nobody should be surprised with this. We get pretty intense energy from the sun during the summertime. Now, when we actually get to our equinoxes, you'll see that the sun is lower in the sky. And it's actually probably right about 50 degrees or a little bit less. And if we get to the winter solstice, in fact, the sun will be right at about 25 or 26 degrees above the horizon. Now, the other thing I want you to notice is the size of these arcs. And you'll see that the mid-latitude arc is much, much larger on the summer solstice than it is during the equinox, than it is during the winter solstice. So not only is the sun lower in the sky as we move from summer to winter, but in fact, these arcs actually are indicative of our daylight period. The daylight period is getting shorter as well. So here in Bowling Green, on June 21st, our daylight period is about 15 hours. When we get to the equinoxes, and we'll talk about why this is so in a little bit, but when we get to the equinoxes, our daylight period is 12 hours. And when we get to the winter solstice, our daylight period is only about 9 hours. So not only have we lost 6 hours between the summer and the winter solstices in terms of daylight period, but the sun is much, much lower in the sky. So the intensity of the energy that we receive in December is also much less. And so, not surprisingly, it's going to be a lot colder here in the wintertime. All right, let's move to our bottom one, and that's the North Pole. Now, the North Pole, and the South Pole for that matter, it's kind of exotic in the sense that the North Pole actually experiences 12 hours of daylight, I should say 6 months of daylight and 6 months of darkness. So if you take a look, what you'll see right here on March 21st and September 23rd is that the sun is right on the horizon at the North Pole. And then let's just start on March 21st. So starting on March 21st, the sun will rise above the horizon, and it'll stay above the horizon all the way through June 21st. 24 hours a day, the sun is shining. Now maybe cloudy, but it's daylight. And then from June 21st to September 23rd, the sun starts getting lower in the sky, but it's still daylight every hour of the day until we get to September 23rd. And then at the North Pole on September 23rd, on the autumn equinox, the sun sets. Right? So the sun sets on September 23rd, and basically it stays below the horizon through the winter solstice, and then right through the spring equinox again before it rises. And so the North Pole experiences 6 hours of continuous daylight and 6 hours of continuous darkness. Now, in reality, it experiences a little bit more daylight than darkness as we move towards the equinoxes because the atmosphere refracts the energy from the sun, and so you get a lot of twilight light even when the sun is below the horizon before the spring equinox and after the autumnal equinox. So it's not exactly 6 daylight, 6 darkness. It's a little bit more light than it is dark in terms of energy from the sun, but I think you get the idea. One last thing about the equator, if we're talking about daylight periods, and what you'll notice is that basically the size of the arc is the same throughout the year. And so the equator, interestingly enough, the equator experiences pretty much 12 hours of daylight and 12 hours of darkness every day of the year. And so the difference between the maximum and minimum daylight periods during the entire year increases as you move from equator to pole. So at the equator, it's always 12 hours. By the time you get to 45 degrees north, it's about 15 hours of daylight in the summer, 9 hours in the winter, and by the time you get to the North Pole, it's 24 hours of daylight during the summer and nothing at all during the winter. So the seasonal cycle and the daylight period and the angle of the sun above the sky all are governed by the seasonal cycle that we took a look at in figure 3a2. Now let's move back to figure 3a2, and I'm going to just start to actually focus a little bit more now on the equinoxes and the solstices. And this is where I'm going to go back to some old school AMS figures, and you'll see why the AMS kind of removed them from the investigations. They're not particularly good figures, they're kind of blurry, but I'm going to use them and enhance them a tiny bit so that you can kind of get an idea of what things look like just from a different perspective. So let's go back to the autumnal equinox on September 23rd. Now what I'm going to talk about here is going to be good or valid for both the autumnal equinox and the vernal equinox, which is the spring equinox. So just to remind you of what I said a few minutes ago, on the equinox, the sun shines directly overhead at the equator at whatever point on the earth it's noon at that moment. All right, so the axis is oblique to the sun. Neither hemisphere is pointing toward or away from the sun. All right, both hemispheres are basically oblique to the sun. So the sun shines directly overhead at the equator. Now let's take a look at what this would look like if we actually take a look at a satellite image of the Earth. So this is from the AMS. They used to put this in investigations all the time. This is a very old, full disk, visible satellite image of the planet. And as you can see, the quality is not great. So I'm going to have enhanced this a little bit. And so first of all, again, this is going to be the 23rd of September. I've put in a sun symbol here. So here's a starburst or a sunburst. Here is the equator. The equator, and you got to follow this very carefully, it is a faint white line that goes horizontally right across the middle of the planet. Now I'm going to click on my PowerPoint, and I'm going to bring up the axis. All right, so here is the axis, and the Earth is rotating about its axis once every 24 hours. Now I'm going to remove the axis for a minute, and I want you to just take a look at this white dashed line which was beneath the axis. This white dashed line is something that we refer to as the terminator line. It is the terminator. It is basically the line that separates daylight from darkness. So everywhere to the left of our terminator is daylight. Everything to the right of the terminator is night. So half of the disk is in daylight, and it is basically shadowing the other half of the disk that is in darkness, the other half of the planet that is in darkness. Okay, now I'm going to put on the axis again. Now what I want you to note is if we take a look at every latitude on the planet, and in this case, the axis and the terminator are identical, what you'll see is that every latitude is half in daylight and half in darkness. So as the Earth is rotating about its axis, and it's basically rotating counterclockwise about its axis, half of every latitude will always be in the daylight and half of the latitude will be in darkness. Over the course of a 24-hour day, what that ultimately means is that every latitude, every location is going to experience half daylight, half darkness. 12 hours of daylight, 12 hours of darkness. That's true here in Bowling Green on this day. We experience 12 hours of daylight, 12 hours of darkness. Equal daylight, equal darkness, equinox. That's where we get the equinox from. So on the equinox, every location on the planet, in fact, it's just a little bit different close to the poles, but we're going to ignore that. So basically for our purposes, every location on the planet on the equinox experiences 12 hours of daylight and 12 hours of darkness. It doesn't matter whether you are in Bowling Green or on the equator or in the southern tip of South America. All these locations, we all experience 12 hours of daylight, 12 hours of darkness. All right, let's move 90 days into the future, and let's move from September 23rd to December 21st. Here's the sun, still shining directly overhead on the planet, but what you'll notice now is that because the northern hemisphere is tilted away from the sun, the southern hemisphere therefore tilted towards the sun, what you'll see now is that the sun shines directly overhead in the southern hemisphere. Not only does the sun shine directly overhead in the southern hemisphere, but if you take a look at our terminator, And here's our equator. Here's this dark band right across the middle of the planet. What you see is on December 21st, the southern hemisphere is experiencing more daylight than the northern hemisphere because the southern hemisphere is tilted towards the sun and the northern hemisphere is tilted away. Conversely, if we take a look at the nighttime part of the Earth, you'll see that more of the northern hemisphere is in night and less of the southern hemisphere is in night, right? So at the end of the day, half of the planet is still illuminated, half of the planet is in darkness, but it's disproportionate. More of the southern hemisphere is in daylight, more of the northern hemisphere is in darkness. And the sun shines directly overhead in the southern hemisphere. So what we're going to see is our daylight periods in the southern hemisphere are going to increase, our daylight periods in the northern hemisphere are going to decrease, and again, that directly overhead point is now going to be in the southern hemisphere. So let's take a look at the planet now. First of all, here's my starburst, but the sun no longer is shining overhead at the equator. The equator is up here, and we'll talk about that in a moment. The sun shines directly overhead now at 23.5 degrees south, and you can see that this is the Tropic of Capricorn. The Tropic of Capricorn is located at 23.5 degrees south latitude, and it is defined to be the southernmost latitude over which the sun shines directly overhead. All right, so where the sun shines directly overhead. So when you go south or poleward of the Tropic of Capricorn, the sun never shines directly overhead. And in fact, the closer you get to the South Pole, the lower the sun will be in the sky on the summer solstice in the southern hemisphere. All right, so again, the sun shines directly overhead at the Tropic of Capricorn on the 21st of December. This is the summer solstice in the southern hemisphere. It is the winter solstice in the northern hemisphere. Now here is the equator. And now the equator is no longer going straight across our screen. You got to follow this faint white line, and you'll see basically that it is tilted from upper left to lower right on the planet. So here's the equator where my cursor is. And so what I'm going to do now is I'm going to put in the axis, and you can see the tilt of the southern hemisphere toward the sun, the northern hemisphere away from the sun. Our white dashed line is our terminator. So everything to the left is in daylight, everything to the right is in darkness or night. Now, to see that more of the southern hemisphere is in daylight on the 21st of December, I'm going to take my cursor, I'm going to move it along the equator, and I'm going to move it down the terminator. And you can see that more of the southern hemisphere is in daylight than is in darkness. Now, if we take a look at the northern hemisphere, all we do is we again move our cursor along the equator, and then we move it up the terminator in the northern hemisphere, and you can see now that we just basically have a pie-shaped wedge of daylight. And the lion's share of the hemisphere is in darkness in the northern hemisphere. So the winter hemisphere is the dark hemisphere. The summer hemisphere is the daylight or the lighter hemisphere. Okay, just want to point out one other thing now that we actually are talking about a solstice. If you take a look at the Antarctic Circle is at 66.5 degrees south. If you rotate the Antarctic Circle about the axis, you'll note that the Antarctic Circle, oops, I clicked that accidentally, the Antarctic Circle never reaches the terminator as it rotates about the axis. So from the Antarctic Circle to the South Pole, it's daylight 24 hours a day on December 21st. If we move into the northern hemisphere, the Arctic Circle is at 66.5 degrees north. It's right here. You can see it's skimming the top of the page. Now, if you take a look at the Arctic Circle, and again you just rotate about the axis, what you see is that from the Arctic Circle north to the North Pole, it is dark 24 hours a day. So during the summer solstice in the southern hemisphere, the highest latitudes have perpetual daylight. And in the northern hemisphere, the highest latitudes have perpetual night. All right, now we're going to move 6 months into the future, and we're going to move right to our summer solstice here in the northern hemisphere. Again, the sun has no idea what's going on the Earth. All the sun is doing is it's shining directly overhead on the planet. Half the planet is in daylight, half the planet is in darkness. But now what you see is that the northern hemisphere is tilted toward the sun. The southern hemisphere is tilted away from the sun. So basically what we're going to see on June 21st is a mirror image, basically the exact opposite of what we had on December 21st. Now on June 21st, the northern hemisphere is the daylight hemisphere. The southern hemisphere is the nighttime hemisphere. The sun now is going to shine directly overhead in the northern hemisphere instead of the southern hemisphere. So everything basically is going to be reversed between the two solstices. So let's move on to our next figure. So this is the planet on June 21st. Here's my starburst. Here's the sun shining directly overhead, and now it shines directly overhead at 23.5 degrees north, which is the Tropic of Cancer. The Tropic of Cancer is defined to be the northernmost latitude at which the sun shines directly overhead. The sun never shines directly overhead north of Tropic of Cancer. All right, so as you move north from the Tropic of Cancer during our summer, the sun gets lower and lower in the sky at noon. And again, like I said, here in Bowling Green, about 72.5 degrees above the horizon. And by the time you get to the North Pole, it's only about 23.5 degrees above the horizon. So even though the pole is experiencing 24 hours of daylight, so here's our high latitude, and you can see it never reaches the terminator, which is, here's our axis, by the way. Here's the terminator. And so what you see on the summer solstice is our highest latitudes in the northern hemisphere now are perpetual daylight. Highest latitudes in the southern hemisphere are perpetual darkness. So literally, there's a complete role reversal between the northern and southern hemispheres between the winter and the summer solstices. And now if we take a look at the Tropic of Cancer and the equator, here's the equator. Now it's right here. I'm going to just move my cursor along the equator. And if you take a look at the equator and the terminator, you can see now that the northern hemisphere is dominated by daylight. Here's the equator and the terminator. And the southern hemisphere is now dominated by night. So again, just study these figures. Again, these satellite images are pretty darn awful, but they are very useful. I mean, they are really useful if you just sort of follow what it is I'm saying, and it kind of just illustrates the seasonal cycle between spring and summer and fall and winter. All right, and I'm just going to show figure 3A1 again, just so you can see how the angle of the sun varies over the course of the year at noon at the equator, at 45 degrees north, and at the North Pole. And so this all basically comes together from those three satellite images that I showed previous to this slide right here. Now, if we take a look at how the sun varies in the sky, this also has a big impact on the amount of energy that makes it down here to the Earth's surface. So basically, energy that comes into the atmosphere from the sun is a function of two variables. The first one is the angle of the sun in the sky above the horizon. So the higher the sun is in the sky, the more energy we're going to get from the sun. And that's basically because the sun has to go through less atmosphere, and it is at a lower angle, or I should say at a higher angle in the sky. Basically, the energy is more concentrated. So what you can see is we get a lot of energy at the equator throughout the year. If you take a look at the mid-latitudes, we get a lot of energy during the summer, but less during the winter. And if you take a look at the North Pole, we get none during the winter, and we get energy during the summer. Now that's factor number one. The second factor is the actually daylight period. So even though we get an immense amount of energy from the sun at the equator, the daylight period is pretty much 12 hours throughout the year. At the mid-latitude location, even though the sun is lower in the sky, our daylight period during the summer is longer and less in the winter. So you'll see in a moment that we actually get a tremendous amount of energy here in the mid-latitudes from the sun during the daylight period in the summer because our daylight period is longer even though the sun is lower in the sky. The big surprise is going to come at the North Pole. In fact, the North Pole, what you see is the sun never really gets high in the sky. So even on the summer solstice, the sun's only about 23.5 degrees or so above the horizon. It's pretty darn low in the sky. But because the sun is above the horizon 24 hours a day, basically you're getting energy all the time. And when you add it up, it turns out to be a fairly big number. So here's our last figure in the investigation, figure 3A3. So what we're taking a look at now is monthly solar radiation at the top of the atmosphere. This is the amount of energy that's coming in at the top of the atmosphere from the sun. The equator is in blue, mid-latitude is in orange, North Pole is in gray. On the x-axis, we have months. So basically what we're looking at for each of these three latitudes is the amount of energy added up that basically comes in from the sun for each of these months for each of these three latitudes. And so this is kilowatt hours per meter squared per day. So, but it's by month. So what we see, let's just start with the North Pole. So you see, actually no, I think I'm going to start the equator. I'm gonna cheat. I'm going to start the equator. Let's start the equator. Remember that the sun is always high in the sky at the equator. And I want you to note, again, that if you take a look at our blue curve, you can see it's pretty high up the entire time. So the equator is always getting a lot of energy from the sun. And you'll see that the equator actually has two peaks. It has a peak right around the equinox, has another peak right here in the autumn around the equinox. So this is when the sun is directly overhead the equator. It happens twice a year. Spring equinox, autumn equinox. So you get two peaks, and then you get two little dips, or two little minima in the winter and the summer. All right, so interestingly enough, what we see at the equator is that the seasons at the equator really are not temperature driven. The equator always receives a lot of energy from the sun. It's just that it receives a little bit more near the equinoxes when the sun's directly overhead, and a little bit less during the solstices when the sun is slightly lower in the sky. Now let's move to the mid-latitudes where we live. And what you'll see, starting at the beginning of the year, not surprisingly, in the middle of the winter time, we don't get a lot of energy from the sun. But what you'll see is that as our daylight period increases and the sun gets higher in the sky, not surprisingly, as we move through the winter into the spring and into the summer, we get an increasing amount of energy from the sun. And sometime, in the April-May period, what you see is that the amount of energy coming in from the sun at our mid-latitude location is actually greater than it is at the equator. So this isn't because the sun is higher in the sky, it's because our daylight period here in the mid-latitudes is actually greater than it is at the equator. By the time we get to the summer solstice, remember, our daylight period here in Bowling Green is about 15 hours, while it's only 12 hours at the equator. And then, not surprisingly, what you see is that as we move from summer into fall, the sun gets lower in the sky, our daylight period decreases, and very quickly we lose energy as we head through the fall and into the winter. Now, let's take a look at our North Pole example. So, not surprisingly, in the middle of the winter in the North Pole, nothing's coming in. But you'll notice that a tiny bit of energy begins to bleed in during February and March, even though the sun is still below the horizon. And that's because the atmosphere actually refracts energy from the sun, we begin to get a period of dawn, and we begin to get energy coming in from the bottom, even though the sun is not completely above the horizon. So we begin to get an extended twilight leading up to dawn at the equinox. And so we actually just get a little bit more than zero. And then, of course, once the sun is above the horizon, then you can see that very quickly the amount of energy coming in at the North Pole increases. Now, it's not much because the sun is not high in the sky, but we have 24 hours of daylight. Oops. And as the sun gets higher in the sky, even though, again, it never gets terribly high, what you see is that because we have 24 hours of daylight, that ultimately, just like in the mid-latitudes, the North Pole ends up receiving more energy per day than the equator. And at the end of the day, pardon the expression, it actually receives quite a bit more energy per day than the equator. And again, it's not because the sun's higher in the sky, it's because it's daylight 24 hours a day. And so once we get past the summer solstice, at the North Pole, the sun gets lower in the sky, even though it's still daylight 24 hours a day. And you can see that it really begins to plunge. So as the sun heads towards the horizon, and the sun angle gets closer and closer to zero, then you can see that our energy coming at the North Pole really plunges. And then we have this extended period of twilight that goes into October, and then we just flatline. It's just perpetual night from there on out, and the sun gets, or I should say the North Pole gets nothing from the sun. So you can see that this annual cycle of energy coming in from the sun is very, very small at the equator. And then as you move from the equator towards the pole, the cycle gets larger. So the magnitude of the difference between the minimum in the winter and the maximum in the summer gets bigger as you head towards the pole. And by the time you get to the North Pole, you go from 0 to a very large number and then back to 0 again. So that's a lot of information about the annual cycle, and that's pretty much all I'm going to say about it here. There is a lot. If you have any questions about anything that I've said here about Investigation 3A, by all means, post something to the discussion board, or feel free to ask me live during my office hours in Zoom. But that is it. That is all. It's everything I'm going to say about Investigation 3A. So I'm going to end now, post this on YouTube, and you'll see an announcement pop up when it's ready for you to view.